All right, imagine for a second that the entire universe is just a giant cosmic cookbook. What if I told you we have the recipe? A list of ingredients and the rules that tell them how to combine to make, well, everything. Today, we're diving into exactly that, the standard model of particle physics. So, let's get started. I mean, it's the biggest question you can possibly ask, right? You've probably wondered about it yourself. What is all this stuff around us actually made of, and what holds it all together? It's a puzzle that has kept the greatest minds busy for centuries. And the answer, or at least the very best answer we have so far, is this incredible theory. It's so successful, so powerful, they just call it the Standard Model. Think of it as our theory of almost everything. It lays out the fundamental particles and the forces of nature with just, well, stunning accuracy.
Okay, so sticking with our cosmic recipe idea, what's the first thing you need for any recipe? The ingredients, of course. And in our universe, the ingredients are the fundamental particles of matter. So let's take a look inside the cosmic pantry.
So it turns out all the matter that you can see and touch, everything, is built from just two families of particles. First up, you've got the quarks. You could think of them as the social butterflies of the particle world. They're always clumping together to make bigger things, like protons and neutrons. And then you have the leptons. These guys are a bit more independent, kind of like the electron, which you've definitely heard of.
So, let's zoom in on the quarks. They come in 6 different types, which physicists, in a moment of pure genius, decided to call flavors. And no, they don't taste like anything. You've got up, down, charm, strange, top, and bottom. Seriously, those are the names. What's really cool is how they're organized. They come in 3 pairs, or generations, and each generation is basically just a heavier, more unstable copy of the one before it.
And you know what's wild? The lepton family follows the exact same pattern. There are 6 of them, again, sorted into 3 generations. The first generation, that's our everyday stuff. The electron and its super lightweight, kind of ghostly partner, the electron neutrino. Then the next 2 generations are just heavier, bulkier copies of the first. You get the muon and its neutrino, and then the even heavier tau and its neutrino.
Okay, so we've got all these particles with frankly weird names. How in the world do they make up, well, you, or the chair you're sitting on right now? It's all about how they combine. For instance, take a proton. It's in the nucleus of every atom in the universe. What is it? It's just 2 up quarks and 1 down quark, stuck together. That's literally it. That simple little trio is a fundamental building block of, well, everything we can see. All right, part 1, check. We have our ingredients. But, just throwing flour, sugar, and eggs in a bowl doesn't magically make a cake, right? You need to mix them, bake them. There are rules. Same thing here. Particles don't just assemble themselves. They need forces, the rules of the game, to tell them how to interact. These are the fundamental forces of nature. Now here's where things get a little weird. In the quantum world, a force isn't some invisible hand pulling things. Instead, forces are carried by other particles. These force-carrying particles are called gauge bosons. The best way to think about it is like 2 people standing on ice skates. If one throws a basketball to the other, what happens? They both get pushed apart. The basketball itself is carrying the push. That basketball, that's the boson. So, the Standard Model covers 3 of the 4 big forces. First, you have the strong nuclear force. Its messenger is the gluon. And yeah, it literally glues quarks together inside protons and neutrons. Then there's electromagnetism, carried by the photon. That's responsible for everything from light to static electricity. And finally, the weak nuclear force, with its W and Z bosons, which handles things like radioactive decay. But wait a minute. What about gravity? Yeah, that's the giant elephant in the room. The Standard Model, it just doesn't include gravity. We have a name for its theoretical particle, the graviton, but it's not part of this picture. So how do physicists even visualize this stuff? Well, they use these little maps called Feynman diagrams. They're like cartoons of particle interactions. What you're seeing here is a story. Time flows from the bottom to the top. See that muon coming in? It spits out a W boson. That's the messenger for the weak force, and boom, it turns into a neutrino. But that W boson is super unstable. It barely exists before it decays into an electron and an antineutrino. It's a whole little drama, playing out in a fraction of a second. Okay, so let's recap. We have the ingredients, the matter particles. We have the rules, the forces that tell them how to interact. Seems like we're done, right? Not quite. There's a giant, glaring question we haven't answered. Why do any of these particles have mass? Why do they have substance?
Because without mass, every single particle would just fly around at the speed of light. No atoms, no planets, no us. The universe would be a very different and very empty place.
The answer is, well, it's one of the most mind-bending ideas in all of physics. It's called the Higgs field. Just try to picture this. The entire universe, every inch of empty space, is filled with an invisible energy field. It's everywhere. Now, as particles travel through this field, some of them interact with it. They get stuck a little bit. That stickiness, that resistance to being moved, that's what we call mass. So a really heavy particle, like a top quark, is like trying to wade through super thick cosmic honey. A light particle, like a photon, doesn't feel the field at all. It just zips right through. That's why it has no mass.
Okay, great. An invisible field that's everywhere. How on earth do you prove that exists? Well, you have to find its particle. Remember how the photon is the particle of the electromagnetic field? Well, the Higgs field has a particle too, the Higgs boson. You can think of it as a ripple or a little clump in the field itself. Finding this thing was the absolute last piece of the Standard Model puzzle, and after decades of searching, in 2012, physicists at CERN finally found it. It was a huge, huge deal.
And this right here, this is what that discovery looked like. It's the moment of truth. Now, you don't actually see a Higgs boson. The thing is so unstable it decays almost instantly. So what scientists look for is the smoking gun, the specific shower of other particles it explodes into. They see these tracks, they measure their energy and direction, and they work backwards. By piecing together all that evidence, they can prove that for one tiny fleeting instant, a Higgs boson had to have been there.
So there you have it. Let's put all the pieces together. We've got the matter particles, we've got the force carriers, and we've got the Higgs to give them mass. This is it, the complete Standard Model, and it's probably the single most successful theory in the history of science.
And here's the whole shebang, all on one chart. Look at that. On the left, you've got your 12 matter particles, which scientists call fermions. Those are your quarks and leptons. And on the right, you have the force carriers plus the Higgs. Those are called bosons. And this ridiculously tidy chart, it explains the fundamental workings of pretty much everything you've ever interacted with in your entire life. It's just incredible. And look, when I say this theory is successful, I am not kidding around. The predictions it makes have been tested again and again and again for 50 years. And every single time, the experiments confirm the theory to an absolutely mind-boggling degree of precision. Its power to predict reality is just, there's no other word for it, astonishing.
Check this out. This is a perfect example of what I'm talking about. Don't worry too much about the details of the graph. All you need to know is that the exact shape of that peak, right there, depends on how many different types of light neutrinos there are in the universe. And look at the data. Those little dots, they fall perfectly on the line predicted for exactly 3 types. Not 2, not 4, 3. The theory said there should be 3, and the universe agreed. That is just beautiful. So yeah, the Standard Model is an absolute triumph. It's the best description we have of the subatomic world, period. But you know how this works in science, right? Every great answer just leads to even bigger questions. So, is this it? Is this the final word on reality, the complete recipe?
Well, the answer to that is a hard no. As incredible as the Standard Model is, it's definitely not the whole story. It has some huge gaps. For starters, what about gravity? It's completely missing. Also, astronomers tell us that everything we've talked about today, all these particles, they only make up about 5% of the universe. The other 95% is dark matter and dark energy, and the Standard Model has absolutely nothing to say about them. And even with mass, okay, the Higgs field gives things mass, but why do the particles have the specific masses they do? Why is a top quark almost as heavy as a gold atom, while an electron is practically weightless? The model doesn't tell us. So you see, the Standard Model isn't the end of the book. It's a masterpiece for sure, but it's really just the end of a chapter, pointing us toward the even deeper mysteries that are still out there, waiting to be solved.